Welcome back, ladies and gentlemen, to another JLand Bio exclusive video. Today we are going to be focusing on Newton's laws of motion. So you probably are familiar with the work of Isaac Newton. You've probably seen images or videos of him sitting under an apple tree, and then an apple falls on his head and he comes up with the concept of gravity. Well, things work a little bit differently to that particular idea when Newton was trying to determine his laws of motion. So we're going to dive into that a little bit today and discuss some of the details associated with it. So hopefully by the end of this video, you should be able to understand inertia and calculate acceleration. You should also be able to examine how forces between interacting objects are related to one another and explain conservation of momentum using Newton's laws. Let's go ahead and start by talking a little bit about Isaac Newton now. In 1665, Sir Isaac Newton began working on his laws of motion, and he came up with 3 of them. And they're pretty straightforward. If you think about how objects move, then you can probably figure out exactly what these laws of motion might pertain to. The first law of motion states that an object moves at a constant velocity unless an unbalanced force acts on it. So, for example, an object at rest is going to remain at rest. Even though it has no velocity, the velocity being 0, it is still a constant velocity. The ball is not going to just spontaneously move one direction or another unless another unbalanced force acts upon it. So the example here on the right is that the individual is kicking the ball. An unbalanced force acted upon the ball, causing the ball to move. An object in motion will continue with constant speed and direction unless acted on it by another unbalanced force. So objects in motion tend to stay in motion until another object or force of an object acts upon it. In this instance, the ball will continue to go with the same velocity until it hits the back of the net, in which he scores a goal. The first law of motion is also called the law of inertia. Inertia is the tendency for an object to resist any change in motion, so you can see how easily it applies to Newton's first law of motion. Consider the diagram on the right. An object with a greater mass has more inertia. It's going to take more force to change that particular motion, so if an object is larger, it has more inertia and requires more force to be able to push that ball. Also consider the car. The object on the top is not attached to the car whatsoever. As soon as the car stops, the object continues in motion as well. So inertia is the tendency of an object to resist any change in motion. As the car stops, the object at the very top continues to move in a forward direction. So you can see how these things apply when we're talking about inertia. The inertia of an object is related to its momentum. Therefore, the larger mass of an object has, the more momentum and more inertia it's going to have. Simply put, if something has more mass, it's more difficult to move it. It will have more inertia and therefore will be more difficult to move. When you throw a ball versus tossing a ball, you exert a larger force on the ball, and this results in greater acceleration. Newton's second law basically states that an object's acceleration is in the same direction as the net force of the object divided by its mass. So if you apply the same force to something that is small, it is going to have a much larger acceleration than applying the same force to an object that has a larger mass. If you apply that same force to a larger mass, it will have a small acceleration, and if you apply that same force to a smaller mass, you'll have a larger acceleration. It's simple math. So Newton's second law of motion can actually be written as an equation, where the acceleration of an object is equal to the net force divided by the mass. The force will be in newtons, and the mass will be in kilograms. Acceleration unit is meters per second squared. You push a wagon that has a mass of 12 kilograms. If the net force on the wagon is 6 newtons, what is the wagon's acceleration? Well, let's remember our formula. Acceleration equals force over mass. We want to know the acceleration. We're given the force, and we're given the mass. So, let's divide. 6 newtons over 12 kilograms equals acceleration 0.5 meters per second squared equals your acceleration. Again, just another problem where we can simply plug in our numbers and solve for our unknown. Newton's third law of motion states that when an object exerts a force on an object, the second object exerts a force that is equal in strength and opposite in direction. Now, this is a little bit more difficult to visualize because typically when we apply a force on an object, the opposite force is with the Earth, and it's very, very difficult to see the Earth move due to that because the Earth is massive. But a good example is actually when you get off of a boat. So when you get off of a boat, you have a force You're exerting a force going one direction while the reaction is the opposite direction. Same thing when you row a boat. When you row a boat, you apply force one direction, but the boat actually moves in the equal and opposite direction. Think about what happens in a crash when utilizing Newton's laws. Let's say you're not wearing your seatbelt. Well, if you're not wearing your seatbelt and the car stops, you continue to move because a force is not acted upon you to stop yet, until your head goes through the windshield. But if you are wearing a seatbelt, we can consider Newton's laws as well. When the car stops, the equal and opposite force goes the opposite direction, pushes you, the seatbelt, into you. So when you push into that seatbelt, an equal and opposite force is pushing the seatbelt back into you, thus preventing you from, dying. It's the same with airbags as well. So let's talk a little bit about gravity. Gravity acts as an accelerating force. It is always 9.8 meters per second squared, meaning that if I drop a ball and there's no air, again, impossible, but we deal with it, it will accelerate at 9.8 meters per second. That means that it gains a velocity of 9.8 meters per second every second that it free fall drops. So if we start at 0 velocity, and 1 second it will have 9.8 meters per second velocity. At a time of 2 seconds, 19.6, and we continue increasing the velocity. Now, air resistance is a friction-like force that opposes the motion of objects that move through the air. This depends on the size, speed, and shape of an object. A more spread-out object will experience more air resistance than a compact object. Think about dropping a crumbled-up piece of paper versus a normal, regular sheet of paper. The crumbled-up piece of paper, because it is an object that is not spread out, will experience less air resistance than one that is spread out like a normal piece of paper. So therefore, the ball will actually fall faster than the piece of paper that is not in the ball. Now, terminal velocity is the maximum speed an object will reach when falling through a substance that has resistance. Air does have resistance. Water has resistance. So there's a maximum velocity that can be achieved where no more acceleration will take place, and that is based on the object that the object is falling through. If there were no air resistance and gravity is the only force acting on it, it is said to be in free fall. Think about the weightless feeling you kind of get in an elevator. If the acceleration of the elevator going down was equal to that of the acceleration of gravity, then you would be in free fall. Let's talk a little bit about the law of conservation of momentum. If no external forces act on their group of objects, their momentum does not change. So if object 1 here, with the velocity of 1, collides with mass number 2, which is at rest, the momentum that initially existed in mass 1 is neither gained nor lost after the collision. Some of the velocity is just transferred to object number 2, while object 1 would move in the opposite direction. So long story short, just keep in mind that momentum does not change in objects instantaneously after a collision. Hopefully you got a lot from this. Those are the student learning objectives from the video. Make sure you're able to understand inertia, calculate acceleration, and explain a little bit of the conservation of momentum by utilizing Newton's laws. Have a great day, guys. Make sure you like, comment, subscribe, and make sure you shop that JLand Bio merch. We'll talk to you later. Bye-bye.